Hi, everybody. All right, so we are going to be talking about VSEPR theory today, valence shell electron pair repulsion theory. And what that is just basically if we have a dot structure, if we can come up with a dot structure of a compound, and we want to determine the shape of the molecule. So what we're going to be referencing, the handouts that you have, the things that we want to reference is in your guided notes. You have this really big chart here, and what we're talking about are these shapes right here. So the shapes in this chart here, and you also have it on this handout here. Here are the shapes, okay? And so when you're trying to figure out the shape, you want to have this chart out so you can reference. You're going to have to memorize up to this point, okay? So if you have up to 4 total domains around your central atom, you're going to have to know by memory what those shapes are. When you go into an expanded octet, when you have more than 4 domains around your central atom, these shapes, we want you to be aware of them, but you're not going to be tested on these, okay? Another thing to know on this chart that's in your guided notes, you don't need to know hybridization, okay? So hybridization is more of an AP chemistry thing, all right? So when I'm trying to determine the shape of a molecule, I'm going to be looking at this chart. Okay. The other thing we're going to be looking at is something called the bond angle. So the angle between the bonds in a molecule. So if I have, a molecule like this, where I have a middle atom, a central atom, and 4 things bonded to it, we want to determine the angle between the bonds there. Okay. So we're going to be talking about how the total number of domains around that middle atom will affect the angle between the bonds. Okay, so shape and bond angle, that's what we're talking about today. All right. So if the first thing we're going to do is look at the dot structure. So we already know how to draw dot structures. So make sure you know how to do that. So now if I give you a molecule of CO2 and we have its dot structure, the first thing we want to be able to do is determine the shape, and then we want to determine the bond angle. So when you're looking at shape, all you want to do is look at the middle atom. So if you look at the whole molecule has 1, 2, 3, 4 lone pairs, 4 unshared pairs. But when you're talking about molecular shape, all you care is about the number of lone pairs and bonds around the middle atom. So yeah, each oxygen has 2 unshared pairs on it, but that doesn't matter for the shape of the molecule. You want to look at the middle atom. And so what we do is we count the number of bonding domains and the number of unshared pairs, and you have to differentiate when you're talking about shape. So if we look at here, we have 2 bonding domains. And yes, a double bond counts as 1 bonding domain. Same with a triple bond. A triple bond counts as 1 bonding domain. So if we look around the carbon, we have 2 bonds, 2 bonding domains, and 0 unshared pairs, 0 lone pairs, okay? And so if we want to figure that the shape of that is linear, but let's go to our chart. How do we do that? So we go to our chart and we say, okay, well, anytime, it doesn't matter what the molecule is, I have 2 bonding domains and 0 lone pairs, we're going to call that shape linear, okay? So boom, CO2 is linear. So if I ask you the shape of CO2, you'd say linear. But now we're going to be talking about the bond angle. So for bond angle, you don't care about the different types of domains, you just care about the total number of domains around the middle atom. So like for shape, I need to know what types of domains I have. I might have 4 domains, but how many of them are bonds and how many of them are lone pairs? I need to know that to determine the shape. But to determine bond angle, you just care about the total number of domains. So whenever you just have 2 domains around the central atom, the bond angle is going to be 180. And looking at the CO2 molecule, you can kind of see, hey, that's 180 degrees. So whenever you have a linear shape, the bond angle is 180, or whenever you have 2 total domains around your central atom, the bond angle is going to be 180. And now if we look at the model kit, here's the model of CO2, the 3-dimensional model, and you can see that the bond angle, let me get it right, the bond angle is 180 degrees, okay? All right, so let's go back. All right, so now we're going to look at this molecule. This is formaldehyde, CH2O. If again, we're just going to go straight to the dot structure. But if you followed your steps for drawing dot structures, you would end up with this looking thing here, okay? And so now I want to know the shape. So I look at the central atom. I got 1, 2, 3 bonding domains. I have 0 lone pairs or unshared pairs around the central atom. And if I looked at my chart, 3 bonds, 0 lone pairs, that's trigonal planar. But again, let's just double check. 3 bonds, 0 lone pairs, we got trigonal planar geometry. Okay? You might say trigonal, I say trigonal, whatever. Tomato, tomato, it doesn't matter. So trigonal planar geometry, okay? And this is not going to be a 180-degree bond angle because we have 3 domains. We have 3 domains. So now if I'm looking at the bond angle and I'm looking for 3 domains here, 3 domains, I got 3 domains, we want to know, what that bond angle is. Okay, if I had 2 domains, it's 180. 3 domains, it's going to be less than that, right? And so notice it's less than 180. So what do we think it might be? Okay, so planar geometry means that all the elements are in the same plane. So this is actually the 2-dimensional representation here of the molecule is pretty accurate. And so if we look at that bond angle, maybe we can understand that the bond angle would be 360 divided by 3, so 120 degrees. So whenever you have 3 total domains, the bond angle is going to be around 120 degrees. But let's look at the model. So here's the model for formaldehyde. We got our double bond to the oxygen, okay? But if we look at that, right, if we look at that, we got our 120 degree bond angle. Maybe, yeah, right there. Okay. Right. So anytime you just have 3 domains around your central atom, we're going to say 120 degrees. All right, so let's go to SO2. So if you were to follow your rules for SO2, you would get this as your dot structure. Now technically it has resonance, so I drew them, okay? But now let's just look at the shape. So we'll just pick one of the structures here and count bonding domains and lone pairs. So around the sulfur, we have 2 bonding domains, a double bond and a single bond. So 2 bonding domains, 1 lone pair, okay? So 2 bonds, 1 lone pair. So if it was 3 bonding domains, we would call this trigonal planar, but we only have 2 bonding domains. We have 3 total domains, but we have different types of domains. They're not all bonds. So this can't be trigonal planar. It's going to have to be a different shape. So let's go to our chart and see what it's called. So 2 bonds, 1 lone pair. The shape is called angular, or also known as bent. And notice there's 2 times bent shows up. And so, yeah, we call this bent as well. Water is this one, is this bent shape, but they're a little bit different. Okay, so you can say, and so if you want to differentiate between the 2 bent shapes, you could say angular. Okay, but we would say the SO2 molecule is bent or angular. Okay. So we look at, we have our shape, but now let's think about the bond angle. So what did we say up here? If you have 3 domains, 120. Well, how many domains do we have around the central atom? We have 3 total domains. Remember, for bond angle, you don't have to differentiate between bonding domain and lone pair. You can just say, I got 3 domains. For shape, you got to differentiate. But 3 total domains, so we're thinking 120. Okay, so let's go to the model kit. All right, so if we looked at the model for SO2, you got to imagine you got your lone pair of electrons sitting up here, and that's what's bending those bonds down to each other, right? If that lone pair wasn't there and I just had 2 bonds, it would be 180 degrees away. But that lone pair, all the different types of domains repel each other, so that lone pair is going to bend the bond, and that's why we do call it bent shape, or it's going to angle the bond, so we call it angular, okay? But if we notice, that bond angle is very similar to that bond angle from the formaldehyde. So here is the formaldehyde, and then here is the SO2 molecule, and we notice that bond angle is around 120, because 3 domains is going to give me a 120 degree bond angle. Okay? All right, so now let's move on to 4 domain shapes. So CH4 is one, methane. If you drew the dot structure for methane, it's pretty simple. Okay, 4 bonds, 0 lone pairs. That shape is called tetrahedral, right? So again, we'd go back to our chart. We got 4 bonds, 0 lone pairs. That's tetrahedral shape. Great. All right. But here's where we got to be careful about the bond angle. All right. This is where we're going to have to start memorizing some numbers. Because the way I drew the dot structure in 2 dimensions really is not a good representation of what it looks like in 3 dimensions. So if you just saw this on a test or quiz very quickly and I said, hey, what's the bond angle there? 90% of the students are going to say 90 degrees. 100% of the students are going to say, hey, that's 90 degrees, 90 degrees, 90 degrees. And even after I warn you about this and you're taking the test later on, a lot of you are going to fall for the trap that it's 90 degrees. But remember, it would be 90 degrees if the atoms in the molecule or the domains could spread out in only 2 dimensions, then yes, it would be 90 degrees. But they have 3 spatial dimensions that they can spread out in. So it's going to end up being greater than 90 degrees. So tetrahedral, or 4 domains, ends up with a 109 degree bond. So it looks like it's 90, but don't fall for the trap. It's really 109. Technically it's 109.5, but we'll just say 109, okay? So whenever you have 4 domains, you're going to say the bond angle is 109. And so let me show you the 3D model so you can see that it's actually greater than 90, right? So here we have our methane molecule, and if I turn it so you can see the angle of the bond, that's greater than 90, okay? You can kind of see that it's a greater than 90 degree bond. So don't fall for that trap. Okay, on paper it looked 90 because we're limited in 2 dimensions. We can try to do some different things, shade things, and try to make it look like it's 3 dimensions on a 2-dimensional piece of paper. But we always got to remember, hey, wait a minute, our molecules exist in 3 spatial dimensions, just like us. Okay, because we're made up of these things, right? We're made up of these molecules, and that bond angle is greater than 90. Okay, so you got to remember the tetrahedral angle, 109 degrees. So whenever you have 4 domains, 109 degrees for the bond angle. Okay, all right, so let's keep going. Let's do NF3. So if we drew the dot structure for NF3, this is what we would get. And notice we have 1, 2, 3, 4 total domains around the central atom. So I know that bond angle is 109, 4 domains, 109 degree bond angle. But let's go to the shape. All right, so I got 3 bonds. I got 4 domains, but I don't have the same types of domains I have here, right? This was 4 bonding domains, 0 lone pairs, so that's tetrahedral. So since I have 4 domains, but they're not all bonds, this is going to be a different shape. It's not going to be called tetrahedral. All right, so 4 bonds, 1 lone pair. If we go to our chart, oops. So we're looking at 3 bonds, 1 lone pair. We call that trigonal pyramidal. So for trigonal planar, you have to have 3 bonds and 0 lone pairs. But trigonal pyramidal, you have to have 3 bonds, 1 lone pair. So 4 total domains versus just 3 total domains. All right, so 3 bonds, 1 lone pair, trigonal pyramidal. It makes a triangle-based pyramid. That's why we call it trigonal or trigonal pyramidal. All right, but we have 4 domains. We have 4 domains, so the bond angle is 109, just like the tetrahedral bond angle. 4 domains, 109 degrees. And let's see if we can see the model. Okay, so here's a model of the NF3. Imagine that lone pair sitting on top, pushing those bonds down into that triangle-based pyramid, right? You can see the triangle-based pyramid there. And that bond angle, which again, it kind of looked like 90 on our 2-dimensional piece of paper, it's greater than 90, right? Whoops, let me do that, okay? And it's a very similar bond angle to our tetrahedral angle, all right? 109, okay? All right, let's go to water, H2O. So when you draw H2O's dot structure, you get this. bond angle's kind of looking like 90, but we know it's greater than that, right? Because we have 4 domains. So water's bond angle is going to be 109 as well. We got 4 domains, okay? So it looks like it's 90, but it's greater than 90. It's not 90, okay? But let's talk about shape. It's going to be a different shape because those 4 domains are a different combination of bonding domains versus lone pairs. So we got 1, 2, 3, 4 total domains, but 2 of them are bonds, 2 of them are lone pairs or unshared pairs, and we call that bent shape. So whenever somebody says, "Hey, what's water shape?" It's bent. It is bent. Okay, but let's go to our chart and just see that. So we got 2 bonds, 2 lone pairs. We call that bent shape. There was a movie a long time ago, not a long time ago, I don't know, 5 years ago. It was called The Shape of Water. I've never seen it, but I saw the preview and it said The Shape of Water, and I was like, bent. All right, AKA bent. All right, but 4 domains, 109 degrees. So let's see our water molecule in 3-dimensional glory. So here's our water molecule. So imagine you got a lone pair, 2 lone pairs up there bending those bonds down to each other. Because again, if those lone pairs weren't there, these bonds could spread out to 180 degrees apart. But because those lone pairs are there, they're pushing or repelling those bonds into that bent angle. But notice that angle is greater than 90. Okay? 109. All right, now, I just said 109 for all of those bond angles, but let's look at something here. Technically, when you go from tetrahedral to trigonal pyramidal to bent, notice that the true bond angle actually decreases. So the bond angle for the tetrahedral shape is 109. The bond angle for the trigonal pyramidal shape isn't 109, it's 107. And the bond shape for bent isn't 109, it's 105. Okay? Now you don't need to memorize these different numbers. If it has 4 domains, 109. This has 4 domains, so just say 109. You don't have to say 107. And this has 4 domains around the central atom, so you can just say 109. But if you want to know, lone pairs or unshared pairs take up a little bit more room around that middle atom than bonding pairs. And so it forces the bonds a little bit closer together. So if you have 4 domains and they're all bonds, you're going to space those out to 109 degrees. But if I take one of those bonds away and make it a lone pair instead, I'm going to force the remaining bonds 2 degrees closer. So 109 goes to 107. And then if I take another bond away and replace it with a lone pair, I'm going to push it 2 degrees closer than 107. So as you go from tetrahedral to trigonal pyramidal to bent, you go 109 to 107 to 105. But remember, for all 3 of these, you could just say 109 degrees and be correct. The trap you don't want to fall for is don't say 90, don't say 90, don't say 90, even though it looks like 90. It's not, okay? All right, so I just want to show you an example of a molecule that has an expanded octet and what its shape is, and show you the 3-dimensional thing. And so I'm not going to do all of them, but I'm just going to do one. Okay, so SF4. So if we follow our rules for SF4, we would end up with this dot structure. And if we're coming up with the shape, we'll use our chart. We have around the sulfur, we have 1, 2, 3, 4 bonds and 1 lone pair. So let's go to our chart. It says 4 bonds, 1 lone pair, seesaw. Okay, so the shape is called seesaw. All right. Now, I'm not going to ask you for bond angles because normally when you have an expanded octet, you have multiple bond angles, and I'll try to show you with the 3-dimensional model here, so you can see why we call it seesaw. Like you look at this and you're like, I don't know, why is that called seesaw? I'll show you here in a second, and again, I'll show you the multiple bond angles. So let's go. Hold on. Okay, so here's a model, a 3-dimensional model of SF4. So you got to imagine that lone pair on the top. Okay, right there. And if you notice, we have 90 degrees, we do have a 90-degree bond angle there, but if you flip it there, we got a 120-degree bond angle there. So we have multiple bond angles. So, I would never ask, hey, what are the bond angles in SF4, okay? But let's talk about why we call it seesaw, all right? I don't know if you can kind of see here, but seesaw, teeter-totter, right? There you go. You got your little seesaw going. Or you can flip it like this and and kind of rock it back and forth that way, seesaw. So that's why it's called seesaw shape. It looks like a seesaw in 3 dimensions, okay? It's that simple. Somebody, hey, it's seesaw, okay? So that's how you determine the shape. And it just takes, practice, and you got to get familiar with it. And remember, the ones you will be responsible for are all the ones with up to 4 domains, okay? Anything beyond 4 domains, you want to be aware of them, and we'll do some activities with the model kits and stuff where you might see the different expanded octet shapes. Yeah, that's it. That's how you do it. All right. So hopefully that makes sense to you. So again, you still need to practice your dot structures, but once you have your dot structures, all you need is that chart to figure out the shapes, and you just got to remember bond angles. Whenever you're asked for a bond angle, think about it. Pump the brakes. It's not such an easy question. Because you can imagine a multiple choice question. They say, a multiple choice question is going to be like, here's the dot structure for CH4. What's the bond angle? Choice A is going to be 90 degrees. And 90% of the state on that SOL is going to pick 90 degrees. Because, hey, it looks like 90 degrees. I might make that mistake. You got to pump the brakes when asked about bond angles. Sometimes the bond angles are straight up, what they are on the paper. 180 degrees, 120 degrees. All right, so don't fall for the bond angle trap. It looks like 90, it's greater than 90. When it looks like 90, it's probably greater than 90 because 3 dimensions, not 2 dimensions. All right, have a good one.